Now, having learnt a little bit about phase diagrams, the next logical question that comes up is, why do specific phases actually form? So, is there any rule or any rationale by which we can understand which types of elements will come together to form which type of phases? So, to understand the answers to this type of questions, we need to look a little bit in depth in the periodic table. So that is what we will be doing now. We will talk a little bit about the periodic table. And so as we discuss the periodic table, it will also become obvious to us that which features can actually be used as elemental descriptors when you are trying to make a machine learning model for understanding which phases are forming. And I cannot emphasize this enough. The knowledge of which phases are forming is extremely important in case of almost all of the materials informatics models, because that will give you an idea about what type of crystal structures are there and what type of properties your materials will have. The only places where this is not going to be quite as significant is if you are able to get a training data set which looks at the variation of properties, maybe as a function of composition or whatever it is, within a single phase field. So if you have that much of data within a single phase field, then probably you can ignore the rules of the phase formation, because you know that you are confined in a single phase field, and then directly use the other features in order to estimate your properties. But that does not happen, that will not happen in most cases, and therefore understanding which phases can form is important, and that's why basic understanding of periodic table is quite important. So just to exemplify this a little bit, we were talking about solid solutions in the previous video. So there are actually some empirically observed rules for the formation of solid solutions, and these were set forth by a gentleman by the name of William Hume-Rothery. So Hume-Rothery says that a substitutional solid solution can form when you have an atomic size mismatch between the two atoms that is less than 15%. Thus, you can have complete solid solubility only if the two atoms or the two elements that you are using to form the solid solution have the same crystal structure. Hume-Rothery also says that the electronegativity difference between the two elements forming the solid solution should be bare minimal. And that is because if you have a large electronegativity difference, it means that one of the elements is more or less electropositive and the other element might be more or less electronegative. And so instead of forming a solid solution where the atoms are sitting on a periodic lattice, but they are chemically disordered, instead of forming a solid solution like that, you will end up forming a much more ordered structure, or you will end up forming a compound. And that's kind of the same reason why the solid solutions are more prevalent if the valency of the A and B atoms happen to be same. Now, these substitutional solid solutions are what we call structurally ordered, meaning that they have lattice periodicity, but they are chemically disordered, meaning that there is no particular rule as to which atom is going to sit on which lattice point, and that's why they are called solutions rather than ordered compounds. In addition to substitutional solid solutions, where one atom is actually substituting another, you can also have interstitial solid solutions. And in this case, basically what happens is your solvent atom might get inside the interstitial sites of the crystal structure of your solvent atoms. So the solute atoms get into the interstitial sites of the solvent atoms. So for a situation like this, again, there are some empirical rules. More or less, you can say that the solute atoms should be less than 60% of the solvent atoms. So there has to be a significant size difference. In case of the substitutional solid solution, the size difference was restricted to less than 15%. In case of interstitial solid solutions, the size difference should be in excess of 60%. So you can see what the difference is. However, the other criteria in terms of the small electronegativity difference and the valency, that is going to stay unchanged. So if you are familiar with the periodic table, you can get a good idea of how the crystal structures change across groups and periods. So basically, as you go across and look at different elements, how the crystal structure will change, how the electronegativity will change, and so on. So that is really the significance of understanding the periodic table before we move forward. So this is a periodic table which I pulled up from the Encyclopedia Britannica, and here what you can see is these is actually color coded. So you have got different types of elements shown over here. So right over here, the ones which are in white, these are your inert gases. Then you have got the non-metallic elements. You have metallic elements, and then in between what you have is the transition metal element. On the extreme sides, you have got what we call a main group elements, and so on and so forth. So in case of the transition metal elements, the electronegativities are not that extreme. Usually on this side of the phase diagram, periodic table, you have a fairly high electronegativity, and on this side of the periodic table, you have got fairly low electronegativity. So if we understand this periodic variation of properties, we can understand the rules of bonding and the rules of structure formation based on the periodic table. So let's take a look at the trends in electronegativity, and basically what happens is as you go up in the periodic table or as you move more to the right, the electronegativity is going to increase. So what happens as we are moving towards the right? As we are moving towards the right, we are steadily adding more and more of the electrons in the valence shell. And so in order to form your stable octet, the element will want to grab electrons in order to form the octet, right? So that is why the electronegativity is going to increase on this side. So this is basically how the electronegativity is going to vary across your periodic table. Similarly, you can also find the trends in atomic radius if you look at the periodic table. So as you are going down the different periods, the atomic radius is going to increase because you are successively adding more and more shells of electrons. Similarly, if you go towards the right, you will see the atomic radius is actually going to come down, and that is because as you move to the right of the periodic table, you are not adding any shells of electrons, but as you are adding electrons in the outermost shell, the interactions between the nucleus and the electrons become stronger and stronger, and as a result of that, that outermost shell starts to contract a little bit. And so you have decreasing atomic radius as you move to the right, you have increasing atomic radius as you go from top to bottom. This is another interesting way of looking at periodic table. So here basically what we have are all the crystal structures of different elements shown in your periodic table. And as you can see, some rather interesting trends begin to emerge as you look at this crystal structures. So for instance, you will notice that somewhere over here, you have all of this body-centered cubic elements. Somewhere over here, you have got the face-centered cubic elements, and then to the other sides, you have got the hexagonal close-packed elements. Of course, there are some exceptions. So as you are finding two well-separated regions of the periodic table where the crystal structure is changing, what this starts telling you that here you have certain number of valence electrons, and over here you have a different number of valence electrons, and therefore the concentration of the valence electrons or the number of valence electrons that you've got is going to affect which type of crystal structure forms. And based on that, people actually come up with this term VEC, or the valence electron concentration, which is really nothing but the weighted average of the valence electron concentrations of the different elements. So based on this type of calculations, one can start to predict what type of crystal structure can form, assuming of course that this alloy crystallizes as a single phase. So again, knowing where the valence electron concentration is going to go up, where the valence electron concentration is going to come down, is something that you can get from the periodic table, and that actually has a bearing on the crystal structure of the compounds that will form. You also find that there are some very well-defined trends as far as the melting temperature is concerned. You will see that as you are going from left to right, you see a peak in the melting temperature, and then that's coming down. And similarly, as you are going from top to bottom, you will see that this melting temperatures are increasing. So now note the elements for which the melting temperatures are high, namely things like tantalum, tungsten, molybdenum, zircon, and so on. So if you now go back and look at the crystal structures, you will see that usually the high melting materials are the ones which have got a BCC structure. And this is where you can actually start understanding the combined power of looking at the periodic table and thermodynamics, because really what's happening is the BCC structure is a much more open structure. Okay, so this BCC structure has a packing fraction of roughly 0.68, whereas an FCC structure is going to have a packing fraction of roughly 0.74. So BCC is your more open structure. As you are heating something, you are putting in thermal energy, and that can allow more and more of the vibrations of the atoms. So if the structure is much more close packed, the atoms will have a harder time to vibrate. If the structure is less close packed, like the BCC structure, it's easier to vibrate. And so as the atoms vibrate more and more, what's basically happening is the entropy is going up, because things are getting more and more disordered. And this entropy plays a role in stabilizing the crystal structure. And so that's why usually most of the high melting materials, where the solid phase actually has to exist at high temperatures, the BCC structure is favored. Now, the structure also determines which type of atomic packing is there. So when we look at the packing of atoms, we can think of mainly two different types of packing. So one is a regular arrangement where you have got long-range periodicity, and the other is a random arrangement where you do not have long-range periodicity. Now, of course, there are many different types of regular arrangements. So based on this, you will end up having different types of crystal structures. But by and large, we can think of the solids as being either crystalline solids or amorphous solids. In case of crystalline solids, you have this periodicity. In case of amorphous solids, the atomic arrangement is much more random. So what is the consequence of something like this? So if you think about this, there is going to be a well-defined relationship between the energy and packing of atoms. So let's take the non-dense random packing in the first case. So it's a random packing, and I'm saying that this is not going to be very dense. And let's take a look at it. So this is a type of curve that you might be familiar with, where you are plotting the potential energy as a function of the interatomic separation. So what happens is, if you have a random arrangement, the chances are the atoms are probably sitting somewhere on this curve. In other words, the interatomic separation is larger. And if the interatomic separation is larger for the same number of atoms, the overall volume occupied by the material is large, and therefore the density is low. In case of a regular type of packing, what happens is the position of the atom. So keep in mind that you've got an atom over here and you've got an atom over here when you are looking at the interaction between these two atoms. The position of the atom is going to be decided by whatever results in the lowest energy. And so for two types of atoms, that would be one particular distance. And so then what really happens is you start having a periodic arrangement where each atom is separated from the other type of atom by a regular distance. So since this happens, in order to bring down the energy, what is going to happen now is you are going to have an interatomic separation, which is given by this. So let's call that R0. And this is essentially your equilibrium spacing between the atoms. Okay. So this regular packed structures therefore happen to be much more dense and much more periodic, because the interatomic spacing stays constant and that gets repeated throughout. In case of the random structures, that's not going to happen. So usually what you will find that this dense packed regular structures will also have lower energy, and this random structures like this amorphous type of materials, they have little bit higher energy. So that doesn't mean that this random structures or amorphous materials cannot form. It just means that they are not the most stable configuration of atoms. So there is going to be a relation between the overall energy of the solid and how well the atoms are packed in that particular phase. So at this point, we can now take a number of lessons from the periodic table, the structures of different compounds and phase diagrams. And the first thing that emerges is you are going to have some rather strong linkages between the periodic table, the structure of materials, and the properties. It will also give you an idea as to where you can expect linearity in variation of the properties. So for instance, you will have certain regions in which as you go across the period, the different elements will have identical crystal structures. So those are places where you can probably have continuous solid solubility, and so the variation of properties need not be that abrupt. I'm of course simplifying things, but you get the gist. On the other hand, if you are now getting into a situation where as you are changing the composition by moving across the period, you are tuning the valence electron concentration and you are precipitating a change of the crystal structure. So as the crystal structure changes, the properties changes, and therefore you start having an abrupt variation. And so that becomes one of the origins of nonlinearity as far as our machine learning models are concerned. The other thing that comes out is the asymmetry matters, and now you really start understanding why Willis defined his different rules the way he did. The asymmetry matters because if you have a large asymmetry of atomic sizes, meaning that one element with large atomic size and the other with a smaller atomic size, you tend to form interstitial solid solutions. If the asymmetry is less between the atomic sizes, there is a chance that you start forming substitutional solid solutions. So the type of phase that is going to emerge can also be predicted in part by asymmetry. Now you have to understand that there are lots of features, and it's not really one feature which is going to give you the complete picture. It is usually a combination of all of these features. So that's something you have to keep in mind. To look at another example of asymmetry, when you have very high asymmetry in the electronegativity, meaning that you have an electropositive element and an electronegative element coming together, that is where you end up with the formation of a compound. Whereas if you now take two elements whose electronegativity values are very close together, chances are instead of forming a compound, it might actually end up forming some sort of a solid solution. And if you think about all of this holistically, you will see that this concept of electronegativity will actually relate quite well with the amount of with the strength of the bonding in your material and how much of disorder it can have. So for instance, if you're looking at cases where you've got a very electropositive material, electropositive element and electronegative element, they will bond very strongly, and as a result these will more often than not prefer to stay at the equilibrium spacings, and then the chance of making disordered structures in those type of systems starts becoming progressively difficult. So all of these is designed to provide you with some sort of a physical intuition, which will then dictate how you are going to select the features that describes your machine learning model. So we are going to stop here now, and next time when we meet, we will discuss more on the physical basis for selection of different features for different types of machine learning problems.